already kind of talked about how to interpret the weight, and obviously you've already done a lot of problems that involve the normal force. If I put this box on this table, what direction would the normal force be in? Yeah, perpendicular and up. How about if I put a box on the wall, say, and then I push on the box, what direction would the normal force be in? The normal force on the box.
Perpendicular to the left.
Yeah, good. Not just perpendicular to the wall, but perpendicular and to the left. So the key point is, what is the purpose of the normal force? The normal force is what prevents an object from moving through a surface. Gravity is trying to pull this down through the table, and the normal force is pushing up to prevent that. Or the person here is trying to push this object to the right through the wall, and the normal force of the wall is resisting that. So do normal forces push or pull on the object?
Push.
Only push. Last time we saw that rope forces can only pull. Rope forces can only pull on an object, while the normal force can only push. Notice that the normal force doesn't have to be up. In simple problems, the normal force is up. But in a more complicated problem, it doesn't have to be up. It's just away from the surface. It points perpendicular and away from the surface.
If it's not on the surface, there is no normal force.
That's right. That's another good point. If you're not in contact with the surface, there's no normal force. A lot of students get so accustomed to the normal force that they assume there's a normal force in every problem. Well, if the object isn't in contact with the surface, there's no normal force. When is there a normal force? The normal force arises when it's necessary to prevent an object from moving through a surface. If there's nothing that's trying to drag an object through a surface, then we don't need any normal force to prevent that. Okay, so let's say that we have a 5 kilogram object in an inclined plane at an angle of 20 degrees. There's no friction. Let's find the normal force and the acceleration. So let's make sure we know how to do that. So let's talk our way through that. How can we get started on this?
So first you can draw the vectors, or you could draw a free body diagram first.
Mhm.
There's mg going downwards.
Yeah, there's the weight of the object, which is pointing down. Good.
Normal force is at a sine this.
Like this?
Yes.
Is that what you're thinking? Right. This is a good example of how the normal force doesn't have to be straight up. Here, the way to push away from the surface is to be pushing like this. Good.
And then are we pushing or are we doing anything here?
And that's it. The only things that are here are the ones that I mentioned.
So we need to establish our x and y
Yeah.
axes.
So should we use horizontal and vertical axes? No.
No.
We want to use axes, and we want the x-axis to be parallel to the surface. So I can draw an x-axis here. It's parallel to the surface, and we have to choose our positive directions. Well, probably it'll be convenient here to choose down as the positive direction, since the object is going to be moving down. Okay, well then what?
Now we're gonna separate into components.
Yeah. Well, which of these forces do we have to break into components?
The W.
Okay, and that's the hardest part here. That's the main thing we need to review. So how would we do that?
You make the triangle.
Yeah. You draw the y-axis down from the normal force,
Sounds good?
and yeah.
Good. Sounds good. The key thing is, remember that we talked about this last time. We want to make the legs of the triangle parallel to the axes. We want the legs of the triangle to be parallel to the axes, and this should be the hypotenuse. So one thing we could do is draw this leg of the triangle. Actually, let's draw a whole new picture so we don't get confused here. I'm going to draw a whole new picture just to break this into components. So we can draw this leg that is parallel to the y-axis, and then we can draw this leg that's parallel to the x-axis. And we can get rid of the excess here. So that's one good way to draw this triangle. Another perfectly good way would be to draw this triangle. You can draw the triangle on either side. This also has legs that's parallel to the axis. So either of those is fine. Now, it looks like you guys really have learned this pretty well already. Most students don't do this right. What most students do is this. They try to draw a triangle with horizontal and vertical legs. Can you see how this would be totally wrong here? Because this is the overall weight, but that's supposed to be the hypotenuse, not a leg. So the reason people make this mistake is in the introductory problems, you're usually drawing a triangle with horizontal and vertical legs because your axes are usually horizontal and vertical. But here, our legs should not be horizontal and vertical because the axes are not horizontal and vertical. It's the hypotenuse that's vertical in this case. So don't assume that the legs are horizontal and vertical, assume that the legs are parallel to the axes, and then you'll draw the correct triangle. This is one of the most important skills we'll be talking about. You'll definitely need this a lot as the class goes on. Now what?
Now we have to figure out the degree of the angle in there, and then figure out the
So how would we do that?
component.
How would we figure out that angle?
We'll do the sine. Well, you turn it around, and you have to take the limit of it. We've just learned that like the cosine is on that side and the sine.
Now, before we can take any sines or cosines, we need to figure out what the angles are in here. Maybe you've already done that. We have to figure out some of the angles in here, first of all. This angle down here doesn't do us any good because it's not in the triangle. We can't just use this angle because it's not in the triangle. We need to figure out some of the angles inside this triangle. So how could we do that? Now, this isn't physics, this is geometry. How could we use geometry to figure out one of those angles?
A squared equals B squared and C squared.
That applies here, but that only tells you about the sides. It doesn't tell you about the angles. And we can't use that here because we only know one of the sides so far. By the way, which side do we already know? Yeah, maybe I should have already worked that out. How do I figure this out? That's m times g. So I'll go ahead and do that calculation. So the overall weight here is 49 newtons. But we can't use the Pythagorean theorem here because we only know one of the sides. So how could we find this angle? Well, I'll just give you what, there's two different methods that you can use here. There's the draw a parallel line method, and there's the draw a right triangle method. I'll just go over the right triangle method because I think that's a little bit easier here. We need to draw a right triangle that involves this angle that we know. A right triangle that involves this angle that we know. So how can I draw a line in somewhere that would give me a right triangle that involves this angle? Well, the easiest thing is just to pull this line down over here. And now we've created a right triangle that involves this angle. How does that help us? Well, that tells us this angle. How would we now calculate this angle?
Oh, right.
What would this be?
20 plus 90. 70.
70. This is 90. We know that the two other angles of a right triangle have to add up to 90. So this must be 70. Now that still doesn't help us directly because we need the angles inside the triangle.
So that's 20.
But now this must be 20. That's right. Okay. If you wanted to, you could figure out this angle down here. This would be 70, but we really only need one of the angles. You could figure out this is 70. It's conventional in physics to use the angle that matches the number you were originally given. So usually when you see the instructor solve this, they're going to use this angle and not this one because the 20 matches the number we were originally given. Although if you felt like it, you could just as well use the 70. All right, again, this is one of the most important things we'll talk about today. It's important to be able to quickly move angles around on a picture. This is something, again, you'll need for the whole rest of the course. This is not the main part of the problem. This should be the easy part. So we need to do a lot of these until it's easy for us to move the angles around. Remember, the trick was you can't use this angle directly because it's not in the triangle. So you've got to move it into the triangle. And the trick is draw a new line so that this is part of a right triangle. We just drew a new line so this would be part of a right triangle. And the easiest way to do that for an inclined plane is just extend the weight line down. There's another method here using parallel lines, but I think this is the simplest. So we can just go over this right triangle method. This is, again, really important to understand. Because you're gonna see lots of problems like this where you have to move angles around. They're not all gonna look like this inclined plane problem. So you can't just memorize how to do this. You gotta learn the geometrical technique of drawing a new right triangle. Okay, all right, so now we have these angles, sorry.
If we use that one, it just would have been 70, right?
Pardon me?
If we use the
The
other
other
triangle.
triangle?
Oh, that's a good point. A lot of people would have drawn this triangle instead. That's right. Well, then this angle is inside the right triangle that we would draw. This would be 70. And then again, most instructors would actually go on to figure out that this is 20 because they prefer to use a number that matches the number you were originally given, although it's perfectly valid to use this number if you want to. We can use either of the angles inside the triangle. That's right. So it shouldn't matter whether we ended up drawing the components triangle above the vector or below the vector. This is actually a little bit simpler because now this angle is inside the same right triangle. It doesn't make much difference either way.